Okay, so this is a Brayton cycle for thermodynamics course, ENGR 251 at Concordia University. Let's look at the question. Consider an air standard Brayton cycle with air entering the compressor at 0.1 megapascal and 15 degrees and leaving at the pressure of 1.0 megapascal. The maximum temperature is 1100 degrees Celsius. Assume a compressor efficiency of 100%. That just means isentropic compressor, and a turbine efficiency of 100%. Again, isentropic turbine, which is the default setup for this type of questions. The pressure drop between the compressor and turbine is 15 kilopascal. Determine blah blah blah. Okay, so first of all, since I just did a Rankine cycle, let's go over this again. The key difference between a Brayton cycle and a Rankine cycle is that Brayton uses ideal gas. So we can use ideal gas law. And Rankine cycle, we cannot. We're going to rely on property tables because in Rankine cycle, there's no ideal gas. Okay, so let's draw the diagram. Instead of having a pump, we have compressor because air can be compressed, and we do not pump air, we pump liquid water. So in this case, this is Brayton, since it is ideal gas. So the first component I'm going to draw is compressor. Same thing, there's no boiler here because we do not boil water. Well, we do not boil air, we burn air. So that's called combustion chamber. Turbine is the same. And we do not have condenser. Instead, we have what's called heat exchanger. But those components have the same job. They just work a bit differently in real life. On paper, we can treat them as the same component with same functionalities. Compressor, same as pump. Boiler, same as combustion chamber. Turbine, still turbine. Heat exchanger, we don't call it here. We call it we do call it heat exchanger here. We don't call it condenser, but they have the same job. Again, we're gonna label some thermodynamics terms. Here we got isobaric. Here we have isobaric. I'm gonna put a quotation mark. Why? Just give me a minute. Here, still we got isentropic turbine and isentropic compressor. State 1. Ooh, state 2, 3, and 4. Again, I'm gonna explain those terms. Let's explain all the terms actually. Isothermal. That means delta T is 0, or temperature is constant. Isobaric, P is constant. Let's say T is constant. P is constant. We have isochoric, which we don't have in this problem, but in the next video in auto cycle, we're gonna see that. That means V volume is constant. Isentropic, that means entropy is constant. Okay, so let's put some numbers here. It says air entering the compressor at 0.1 megapascal. Where is that? Air entering the compressor, that's state 1. 0.1 megapascal, just write it down as kilopascal. And the reason why I put a quotation mark on isobaric here between state 1 and state 4 is because of this sentence. It says the pressure drop between the compressor and turbine is 15 kilopascal. Not too sure what exactly it means, but I assume that P4 is P1 minus 15, which is 85 kilopascal. Turbine, we have work out. We got work in for the compressor, Q in at combustion chamber, and Q out at heat exchanger. What else we have? Assume compressor efficiency 100%, turbine efficiency 100%. That just means isentropic. This 1 megapascal value, where is it? Entering compressor and leaving compressor. That means our P2 is 1 megapascal or 1000 kilopascal. P3 is going to be the same because from 2 to 3 is isobaric process. So this is the same as P2. What else we have? The maximum temperature is 1100 degrees. Where is that value? It's at P3. It's at T3, sorry. That's right after the combustion chamber where you will see a maximum temperature here. Degree Celsius, useless. Convert that into Kelvin right away. And that is 1373 Kelvin. Ooh. Okay, so that's pretty much it for the diagram, and we can start solving the problem. State 1. What do we have? We have pressure 1, which is just around atmospheric pressure. T1. Do we have T1? Oh, yes, we do. It says 15 degrees. And that is, in Kelvin, is 288. Almost missed that. Done. So we're gonna need at least 2 independent properties for each state. Once you have 2, you can have more, but you're gonna need at least 2. So that's done for state 1. State 2. We have P2. This is given. How about T2? We don't have T2. The question didn't tell us about T2. However, since this is Brayton cycle, we can use ideal gas law. We can use isentropic relationships. And for isentropic relationships, the prerequisite of using them is having ideal gas in a cycle. If there's no ideal gas, even if the process is isentropic, we cannot use the isentropic relationships. I'm talking about Rankine cycle. But in this case, we can use them. And the one I'm going to use it is this one. T2 over T1 is equal to P2 over P1 to the power of K minus 1 divided by K. What is K? K is 1.4 for air. I forgot the name for K. I think it's some sort of... No, it's not gas. It's not gas constant. Gas constant is R. Let me double check. What's K called? K... It's definitely not Kelvin K. It's another thing. Just give me a minute. I'm also curious. Where is K? You can find this thing in your property table. Well, I see it, but I only see small k. I only see the symbol, I don't see its name. But whatever. Just need to know that for air, the value of k is 1.4. Okay, so now we can solve for T2. Is equal to T1 P2 over P1 to the power of this guy. Plug in some values. T1 we got 288, and P2 divided by P1 is just 1000. Let's put whole numbers here. 1000 divided by 100, or you can put 10. And here is 1.4 minus 1 divided by 1.4. Do the calculation. T2 is 556 Kelvin. Pay attention to the unit. This is Kelvin, not degrees Celsius. Since we got temperature T2, we have all the information for state 1 and state 2. What's sandwiched between state 1 and state 2 is compressor. So right away we can calculate work input. So at the compressor, we have Q minus W12 is equal to H2 minus H1. And since it's adiabatic, why adiabatic? Because isentropic. Isentropic means adiabatic and reversible. So heat is 0. So work 12 is H1 minus H2. Since we're dealing with ideal gas, we can write H1 minus H2 into Cp T1 minus T2. Remember, I'm gonna put it here. Since we have ideal gas, we can use ideal gas law. We can use isentropic relations. That's this formula. This is one of the relations. We can also use Cp, let's say Cp delta T to replace delta H. Okay, let's continue. So work 12, plug in value. Cp for air is 1.004. Temperature difference like you can see, we got a negative value for work 12, which is normal because we are supplying work to the to the compressor. Compressor doesn't do work, it needs work, so that's why work 12 it's negative. Then we can move on to stage 3. Stage 3 we have pressure 3, which is the same as pressure 2 because it's a isobaric process. 1000 kilopascal. We also have T3 that's given. So done. Stage 4. What we have is pressure 4. And that's like 15 kilopascal less than P1, so 85 kilopascal. How about T4? Well, again, we're going to use isentropic relationship to find T4. So T4 is just T3 times ratio of P4 over P3 to the power of K minus 1 divided by K. Plugging values. And remember, P4 is smaller than P3, so this is small divided by big. K is 1.4, and that gives me this much Kelvin. Again, we don't use degrees Celsius here, we use Kelvin. And right away we can calculate the work at turbine, which is work output. Does the turbine do work? Yes. Does the turbine do anything to heat? No. Isentropic, meaning adiabatic, meaning no heat. Swap. Since ideal gas, this is Cp T3 minus T4. Because we don't have H value for those stages. We don't use property tables because the property table is not for air, it's just for liquid water. So we cannot use H because we just can't find any values for H. And since this is ideal gas, delta H can be replaced by Cp delta T. That's a very important, like having ideal gas is the very important prerequisite for using this and isentropic relationships. T3 so work output is this much. Since we got work at the turbine, we also have work at the compressor. Immediately we can calculate work net. Pay attention, I'm still writing small w, this w instead of big W, because we are still dividing by mass. We don't have the mass flow rate here. So work net is just work output minus work input. Work output is work 3, 4. This is turbine minus work input. This is work 1, 2. This is F compressor. And here, very important, I'm going to put absolute value because otherwise your work net will be greater than work at the turbine, which is impossible. You do not do minus minus here. And that's for work output. We kind of forget at stage 3 where we can calculate the heat in. So let's do it here. At combustion chamber, we got Q23 minus W is equal to H3 minus H2. Does the combustion chamber do work? The answer is no. So it's just H3 minus H2. Since this is ideal gas, so Cp T3 minus T2. T3 we had and T2 we got that. So heat in is 820. Now we can compute the thermal efficiency of this Brayton cycle. That will be work net divided by Q in. It's what we get from the system over what we give to the system. Work net is what we get. We get power output. Q in is what we give to the system. We supply heat in the combustion chamber. Plug in values. I got efficiency of 52%. Let's compare that to Carnot. What is Carnot? Carnot is like, it tells you the idealized efficiency, which is the theoretical maximum efficiency. In real life, you are pretty far away from that value. If you see your value that's too close to this value, something's wrong. If you see your value is higher or equal to this value, something is absolutely wrong. Low temperature divided by high temperature. I'm going to use Kelvin. Where is my low temperature? That's at state 1, right here, 15 degrees or 288 Kelvin. How about my high temperature? Highest temperature, that's here, state 3, T3, this is Kelvin. That gives me around 79% of efficiency. Obviously, this is less than, so we're good.